Hi everyone. Let's get started. So today's speaker is Christiane Burton from, she's an imaging physics resident, associated with HMS, Children's, as well as Math General and BI, I believe. So today she'll be talking about addressing limitations of the ACR Dose Index Registry patient size measurement method.
Thank you very much, Liz, for that introduction. So, yeah, I'm from the imaging side. I know you guys are from the therapy side. So I'm happy to be here today to tell you a little bit about the research that's going on at the imaging side. If you have any questions during my presentation, please feel free to speak up in case there's a term that I use that you're not totally familiar with. Okay, so CT dose is a general concern in the medical imaging community, and this is due to the increase in the number of CT examinations and the relative high dose compared to other imaging modalities such as X-ray imaging. And it's always been a challenge for medical physicists and radiologists to keep within the LAR principles. So because of this, a method for dose monitoring was required, and that involves quantifying patient-absorbed dose. So the CTDI ball was introduced for that purpose. It was a really important step in quantifying radiation output. So CTDI ball was adopted into the FDA and Code of Federal Regulations. And specifically what CTDI ball is it measures the radiation, the system's radiation output using a PMMA cylinder that either has a 16 centimeter diameter or a 32 centimeter diameter to represent the head and the body, respectively. The great thing about CTDI ball is because it's a cylinder, the measurements are consistent and reproducible. Now, there was a study that came out in 2011 in radiology which stated that CTDI ball and patient dose are not the same. And that's correct. So CTDI ball measures the radiation output for the system, but it doesn't actually measure the patient absorbed dose. But because the measurements of CTDI ball are consistent and reproducible, ideally a method would be needed to scale the CTDI ball to estimate the patient dose. And this is how the size-specific dose estimate was introduced. So I'll refer to it as the SSCD. So it uses a normalized dose coefficient to actually scale the CTDI ball. So if you want to look at this in equation form, so AAPM Task Group Report 204 came out with SSD equations. And basically what it is the product of the normalized dose coefficient, that F factor, and the CTDI ball. So this F factor is basically like a scaling factor, and it's termed as the normalized dose coefficient, and it depends on patient size surrogates. So if you have an accurate estimate of the normalized dose coefficient, if you have an accurate estimate of the patient size surrogates, you'll have an accurate estimate of the normalized dose coefficient. So what are patient size surrogates? So AAPM Report 204 came out with the geometric patient size surrogates known as, if you look at the image here, you have AP lateral. This is a CT axial image. So you have AP and lateral, and then if you combine the AP and lateral components, you can do it in two ways. So you can take the average of the two or the square root of the product. You'll get a circle of equal area with a diameter known as the effective diameter. So this is an example for the abdomen. Now the problem with these geometric size surrogates is that they don't include patient attenuation. And this is a problem because in a chest scan, a huge caveat would be the lung region where there's a ton of air. And this is a problem because air has lower density compared to PMMA, and this would reduce the patient attenuation from that 32 centimeter CTDI ball phantom. So something like the chest, for example, if we combine the AP and lateral components, could have the same effective diameter as the abdomen. And if you recall, the effective diameter is actually used to calculate the normalized dose coefficient to scale scale the CTD eyeball. So scaling it, what I'm saying here is that the chest and the abdomen would scale it the same way, and this wouldn't be appropriate considering that the chest has the thorax component in the scan. So later on, the APM report 220 addressed this by introducing the patient attenuation surrogate known as the water equivalent diameter. So this was better because the water equivalent diameter, I won't show you the equation, it's a little messy, but all you need to know is that the water equivalent diameter depends on the mean pound-field unit. And so, as you can see here, that circle for the chest is actually smaller because the thorax has a negative pound-field units in it. So if you take the mean of pound-field unit in the CT axial image, it will scale appropriately. So the water equivalent diameter is more appropriate to use when calculating normalized dose coefficient to scale the CTD eyeball. So the issue with so the APM reports 204 and 220 also use Monte Carlo simulations and phantom measurements to generate their results. But there had never been a large-scale study to confirm these results. So this is something that we worked on when I was at the University of Wisconsin-Madison. We wanted to present the first large-scale study using clinical data. Also in these reports, we couldn't find any information on for adult heads. So we wanted to extend our analysis to include head scans. And we found that kind of interesting because head scans are the most common type of CT exam type. And lastly, we wanted to provide measurements of patient ellipticity ratios for different body regions, which I'll explain that soon. So the AAPM reports 204 and 220 recommended that either the center of the scan be used or take an average of the patient-size surrogate over the entire patient, over the entire patient scan. And key studies have shown that there's accuracy for varying SSDE in the Z direction, but they don't account for modulation in the X and Y direction. So what does this mean? So here, this is for a single patient. I'm showing the effective MAS, or dose, as a function of water equivalent diameter. So what I did is I plotted the water equivalent diameter and the effective MAS for each CT axial slice for one patient. And as you can see here, these two CT scans have similar water equivalent diameter, but the dose difference is about 40%. So why is this? I postulated that this is because of the difference in the lateral and AP components of these, the lateral and AP dimensions of this patient, because that changes the path length. So that would change the dose ultimately. And so when I plotted the ellipticity ratio, which is the ratio of lateral over AP, as a function of water equivalent diameter, I found that the ellipticity ratio was significantly different between the two. So, and it's important to note that details on how the CT scanner modulates dose are not widely published. And we think if we were to provide the community with ellipticity ratios for different body regions, this would be important for labs who are actively involved in reverse engineering vendor AAC algorithms for research and clinical purposes. So in our method section, we collected patient CT axial scans for 884 patients. 297 were adult abdomen, 300 chest, 200 head, and 87 pediatric abdomen. I won't go through how we actually did this, but we extracted AP and lateral components from every CT axial image for each patient. And then from there, we were able to calculate the ellipticity ratio, which is the lateral over the AP, as I mentioned, and the effective diameter, which the equations are provided in the APM 204, but there's two ways of calculating them. And separately, we calculated the water equivalent diameter, and that equation is a little bit messy, but this is the one that depends on the mean Hounsfield unit, as I explained before. Go back. And all patient surrogates were averaged over the CT scan. So the APM report 204 said that we should use the center of the scan, but we're going to argue that we should be looking at the entire scan, and I'll show at the end why that should be. Okay, so first thing we did was we wanted to validate the AAPM report 220. So here I'm showing the water equivalent diameter as a function of effective diameter, and as you can see, when I plot every point on there, this is for every patient, the results correlate quite well with each other. You can see the chest data is here, and the abdomen, and the pediatric and the head are down here. So we noticed two things from this graph while we were validating the AAPM reports, is that there were points here that fell outside of these lines, which are the 95% confidence interval. And so we term these points outliers. So in this case, a typical head exam would look like this, but this patient had more bony structures in their head, and so because they had more bony structures, this would increase the mean of the mean Hounsfield unit. So that's why this point falls a little bit above the line. Now over here, this patient had more lung tissue compared to a typical examination, so that's why I pushed that value down, because the water equivalent diameter would be lower as a result. And for this case, I'm not sure what the condition was here for this child, but they had a ton of air pockets in their abdomen, whereas a typical pediatric scan would look like this. So that's why the water equivalent diameter is lower than it should be. So I think overall we did validate the AAPM reports 204 and 220, but we found a few outliers that don't agree with the fit. So the second thing we noticed about this graph, and it surprised me, was that this is a chest scan, and it falls, very well within the fit. And I found that surprising, considering that there's a fairly decent-sized thorax region within these chest scans. So I thought that these values would be a lot lower, not anywhere near the abdomen. So what I did was, just to investigate, I sectioned the chest data. So I sectioned it into abdomen only, and then thorax region, and then shoulders only for each patient. And I plotted the mean of those separately. So over here, you can see the abdomen only, and as I expected, this line and this linear regression agrees quite well with what we find for the overall data. Now the shoulder data, so the shoulders typically have the same water equivalent diameter as the abdomen, but because they are broader, the lateral dimension is larger. So the shoulders have been pushed more to the right. So there's a shift there. Now the thorax region, as I expected, these values would be a lot lower than the abdomen only. So AAPM report, as 204, as I mentioned, said that we could use the center of the scan, but I think that we should be using the entire scan, and we should be looking at it on a per slice basis based on these results, because the thorax region would require a much lower dose compared to taking the mean of the entire scan or just looking at the center of the scan. So then we did a direct validation of the AAPM reports, 204 and 220. They provide fits or data. So AAPM 204, for AAPM 204, we just basically superimposed our fits over there with a 95% confidence interval. And as you can see, when I plotted the effective diameter as a function of patient size surrogate, our fits agree quite well with each other, and they both fall within the 95% confidence interval. So we felt fairly confident that we had validated AAPM report 204. And then for AAPM report 220, they provide points. These points here, the asterisks, are the abdomen only, is for abdomen only, and these points here are for thorax only. So we used our fits and superimposed we plotted their points and our fits, and we found that their points fell well within the 95% confidence interval. So again, we confirmed AAPM report 220 looking at this graph. And so we felt fairly confident that going forward we could extend our AAPM or our analysis to the head. So here I'm plotting the water equivalent diameter as a function of dimension, and this is the lateral effective diameter and the AP dimensions. There's fairly poor correlation between the lateral and AP, and since we combine the lateral and AP to calculate the effective diameter, we'll also have a poor correlation. And this is because in the lateral direction, the ears protrude at different degrees for different patients. And for the AP dimension, the nose protrudes at a different degree for different patients. So that's why there's a poor correlation between the two. And then obviously, if you combine the two, you'll get poor correlation between that and the effective diameter. Oh, sorry, can you go back? And I also want to say that this bit will be used in the next AAPM task group report, 297. So that was the last thing we did is we wanted to show results for ellipticity ratio. As I mentioned, this was really important. So we recorded the mean ellipticity ratio and the standard deviation, and I wanted to get an idea of what the range was for the ellipticity ratios, because AAPM, as I'll just reiterate again, they wanted to use the center slice, but I think that because the ellipticity ratio varies, that we should be looking at the entire patient. Here I'm plotting. I'm showing the min and max range for the two, and you can see for all these cases that the range actually varies significantly, except for the head. So again, this reiterates the fact that we should be looking at the patient on a per slice basis. So just to conclude from the study, we identified sources of outliers that deviate from the AAPM trends. We confirmed both reports and were able to extend it to the head. And we reported the ellipticity ratio for the first time. And this is important because, again, details on how CT scanners modulate dose are not widely published. And a few labs are working on reverse engineering vendor AEC algorithms. Okay, so that was for CT axial scans. Now, ideally, we would want to have information about the SSDE prior to our CT axial scan. So the good news is usually before you do a CT scan, there's two localizers that are acquired, so one in the AP direction and one in the lateral direction. So you can get information on the AP and the lateral dimensions from these CT localizers. Now, AAPM picked up on this and said, if you want to use CT localizers, it's fine, but you need to do a magnification correction for the AP and lateral dimensions. And for now, I'm just going to focus on the effective diameter, because the water equivalent diameter requires a calibration method, and that's ongoing work at the moment. So as you can see here, when the patient, the patient is placed on a table, and the table height varies. So in the vertical direction, this will change the apparent size of the patient. So if the patient moves further away from the source, the apparent size will decrease. It will be smaller. As the patient moves closer to the source, the magnification will magnify the patient, so the apparent size will increase. It's not such a problem from the lateral direction, because you can see that as the table height varies, these measurements don't differ very much. And this is something that the vendor actually doesn't correct for. So, yeah. So the vendor assumes that we want to do a magnification correction, but the vendor assumes that the patient is a flat line placed at isocenter. So So it assumes that the X-ray actually grazes the anatomy at isocenter. But the edges here, this doesn't really represent the edge of the phantom when it's projected onto the image. If you can imagine that this would be the image and this would be the edge of the patient. So this is actually what they assume. Now there's other studies out there by Christensen, Lee, and Rupak that basically they assume that the patient is also a flat line, but that they also take into account the table height. And this is better, as you can see, getting closer to lining up the edges of the patient with the edges of the image. But they assume that the X-rays graze the anatomy at the largest lateral position. And in our magnification method, which I'm going to call the model-based method, we make less assumptions. We assume that the patient is actually an ellipse, and we take into account when the X-rays first graze the anatomy. So you can see here the edges of the patient actually project onto the image where you would find the edge of the patient in the image. So we published a technical note on this. And in this study, we wanted to test our equations. The equations we came up with were fairly messy, really long. So in order to test it, we wanted to do a phantom experiment. And so to do this, we used a 32 centimeter CTDI ball and 21.5 centimeter cylinder water phantom, and we used an elliptical phantom that has 3 different regions. So it has a large and small, a large, medium, and small region. And then we acquired lateral and AP projections. These are CT localizers of all phantoms. And then we measured the lateral and AP measurements from images we used calipers in this case because we were testing our magnification method, so we wanted to get a really precise measurement, so it wasn't like a garbage in, garbage out situation. So we wanted to make sure that the data going into our algorithm or our equations were clean. And then we applied a magnification correction to the lateral and AP measurements. And, in our method, we use DICOM metadata to actually determine what the table height SOD and pixel size would be, whereas the other methods, the previous methods that I mentioned, they would actually try to calculate the table height from the image. So they would do some sort of post-processing to estimate what the table height would be, whereas we're just using data that directly comes from the DICOM header. And then we compared the corrected AP and lateral measurements to the true dimensions, which we knew. So just to give you an example of what the results, how we plotted our results. So this is the lateral dimension. So this is, we performed a magnification correction using the vendor approach, the previous approaches, and our approach. And I plotted them all here. And we varied the phantom. We varied the table height. We had the phantom on the table, and we varied the table height. So for the vendor approach, as you can see here, these squares, the lateral dimension would vary with table height. But the other approaches, because they take into account the table height, you can see that it flattens out the data, but still not exact. So in our approach, because we make less assumptions, these points here line up with this dashed line here, which is the true dimension of the patient. So what I conclude from this graph is that our magnification method, because we make less assumptions, will actually agree with the true dimension of the phantom. And so we did that for all other graphs, for all other dimensions and phantoms. And you can see here for the AP cylinder, again, our results agree quite well with the true value, and similarly to the elliptical phantom, and for both lateral and AP dimensions. And as I mentioned, this is important because we use the lateral and AP dimensions to calculate the effective diameter, and that's used to calculate the normalized dose coefficient, which scales the CTDI ball to get SSDE. So here I'm plotting the normalized dose coefficient using the magnification method, and we're comparing that to the value that we would get using the true dimensions of the phantom. And again, our results agree quite well with the actual value. So our model-based method provided a consistent and accurate result for lateral and AP dimensions. We had a less than 1.8% error for all measurement conditions, whereas for the vendor it was more like 31%, and for Christensen, Rupakanli, it was about 7.5%. And then for the normalized dose coefficient calculations, we had a less than 1.2% error, whereas it was more 17% for the vendor and 5% for Christensen, Rupakanli. And so just to conclude from this study, the model-based magnification correction method is more accurate than the vendor approach. We compared our methods to all previously known reported methods in the literature. And our model-based method requires no actual tomographic CT images. So we only use CT localizer radiograph and DICOM metadata information. And this makes it amenable to large dose registries. Okay, so then once we confirmed that our magnification method worked, we wanted to actually see if it would, yeah.
Oh, sorry. So when you just take the couch group from the DICOM, do you assume there's no space between patient and the couch top? I mean, the reason I ask is in our case, we sometimes have, immobilization devices. If you just take the group from the DICOM, which will put the patient in a different position, so the magnification factor might be as accurate, or is that assumption you think?
So are you saying if you put like?
So like you determine the magnification factor of the patient's size,
right?
That which this function of the table.
Yeah, so we have it on the table. Yeah.
Yeah, but it's actually the function of the patient.
It's actually more.
Not the table height.
Right.
Something in between patient and
yep.
the table.
Yeah.
Yeah. You put your.
Yeah. So what I plotted there on the graph was the distance between the center of the patient. Actually, we can go back to those graphs. Yeah, that's fine. Oh, one more. Yeah. Yeah, the center of the phantom and the isocenter. So yeah, you're doing like a subtraction. So it's like the table height minus half of the AP measurement. In this case, we assume that the AP, we don't do a magnification correction for that AP measurement. We just take that one from the image. So that's the only assumption that we make. We don't do a magnification correction in that case.
It might just not be relevant for diagnostics because patients are just lying on the table. I think for us, our patients aren't necessarily lying on the table.
Yeah.
There's like a big, thick thing between the tabletop and the patient is variable per patient.
Oh, I see. Yeah.
Right, probably cut that.
But probably for diagnostics, they're just on the table. Yeah.
That's a good point. I mean, I could talk to you about that after because that's interesting to me. I mean, if this is something that you wanted to use,
No, I mean, in that case, like probably from the actual CT scan, assuming the factor is actually more appropriate. Like you mentioned, like some other vendor recommend use the image to determine the symptom here.
But then it's too late. Did you already scan the?
Oh yeah, no.
yeah. So yeah, actually, the previous study was just to confirm their results, and then going forward, just made us confident that we could compare ours to I was actually just confirming our extraction method, to be honest, just so that we knew going forward that we could actually, which I'll describe here, is we could use patient data. We were confident that our extraction method for the CT localizers would work, and also for the CT axial images. So.
But did you check your mag factor stuff with actual patient data?
Yeah, that's next. Yeah.
Okay.
So yeah, this is kind of like this is like the grand finale. Oh yeah, no, keep going. Yeah. Okay. So now that we confirmed that our extraction methods for the CT localizers and CT axial scans were good, we could. Okay, so AP. So yeah, we retrieved patient data which had AP and lateral CT localizers and also CT axial scans. We used 280 for adult chest, 229 adult abdomen, and we did some PEEP cases, so we did 48 pediatric abdomen and 12 pediatric chests. So we extracted lateral and AP measurements from both CT localizers and AP and lateral and AP from the CT axial images. We use an extraction method for the CT localizers described by Christensen et al. I'll kind of describe that a little bit. We didn't want to go through each patient and use calipers. We wanted an extraction method that works. So this is actually the ACR DIR method that he describes, and I'll get to that soon. So then we applied a magnification correction for the lateral and AP measurements and the CT localizers, and again we used DICOM metadata, and then we compared the lateral and AP measurements to the true dimensions, which we get from the CT axial scan. So the ACR DIR method is basically used to remove the couch from the image. So basically you just take a sample scout, this is a sample scout in the AP, this is how we extract the AP dimension. And so, yeah, we apply a smoothing and saturation filter to denoise the data, and then we take a line profile through the location of the scout image, and then we apply a 30% threshold. So we just want to exclude the couch from the image. We don't want to factor that into the patient size. And then we just count the number of pixels that exceed that threshold, and then we repeat that for all Z locations along the CT localizer. So we know we can get information on the Z location so that we can exclude this part here. We only want to get the information, and we only want to use the same range as the CT axial scan. Okay, so on your left here, I'm showing the lateral dimension results. So over here is the localizer-based lateral dimension as a function of the gold standard. So this is what we get from doing the magnification correction, this axis here, and this is what we get from using the CT extraction. So as you can see, for a good chunk of data, when we apply our model-based approach, our points agree quite well with this line of unity. So this line of unity suggests that that the lateral dimension that we get for the CT localizer is the same as the CT axial scan, which is what we want. So if our points fall along this line, then that's a good thing. And as you can see here, some of these points here, they were kind of, these were just special cases where the patient had their arm up, and so it was kind of a garbage in, garbage out situation. And all these points here were due to bariatric patients. So the problem with the ACR DIR method, that extraction method that I described, is that if the patient takes up the entire CT scan, it'll actually erode away a lot of that patient. And so because it does that, it'll underestimate the patient size. So that's why these points here kind of fall below that line. And over here, just showing the AP dimension. So this is the localizer-based AP dimension as a function of the gold standard CT axial AP dimension. And for the most part, again, like the points fall along the line of unity. But the problem over here is that the pediatric patient size gets overestimated because the couch doesn't get eroded away as much as it should. So this will actually get included in the entire patient size. So it overestimates the patient size. And again, because we use the lateral and AP measurements to calculate the scaling factor, the normalized dose coefficient, here I'm plotting the localizer-based normalized dose coefficient as a function of the gold standard. So using the CT axial, using the lateral and AP measurements we get from the CT axial image. And this is, again, the line of unity. And our points in black here, for the most part, fall along this line of unity compared to the vendor approach, which does not fall along the line of unity. So, yeah, our results, our model-based approach actually gives us quite accurate results. So just to conclude, on average, the effective diameter for the ACR DIR method, so just using the vendor approach, is about 8% greater than the gold standard, whereas our model-based approach is about 1% greater than the gold standard. And the model-based method, magnification method, gives a more accurate estimate of the effective diameter. and this is needed for normalized dose coefficient calculations to achieve an accurate size-specific dose estimate. And as I showed, the thresholding based size method will fail for large and smaller patients. And just going forward, I know I didn't talk about the water equivalent diameter for the CT localizers because that's ongoing work, but basically the lateral and AP measurements need to be accurate in order to determine the water equivalent diameter after a calibration is done. So going forward, having an accurate estimate of both these dimensions will actually give us an accurate estimate of the water equivalent diameter. So that's sort of where we're headed at the moment. And that's all I have. So if you have any questions, feel free to ask me.
Well, is there a certain way that I estimate from CTDI to the organ dose?
Yeah, that's a good question. So APM stated that we can't use this method to calculate organ dose. And I have not seen anyone attempt to do that yet, but it's a good point.
You have this patient dose, what do you think?
Oh, it's milligray. Yeah. Yeah. Yeah.
So for the pediatric patients, could you like threshold or get rid of the couch just by its position because you know the couch height?
It has more to do with the fact that the patient is just skinnier. And
yeah, but you should know where it falls on the scout, right? Like, could you just automatically not include stuff on that part of it? Like, could you know?
Oh, I know what you mean. Yeah, it's because there's a gap between the like the patient and the couch itself.
No, because of the couch height. So you have the couch height and the DICOM data.
Yep.
Like, so shouldn't that then determine where on the scout image the couch top falls, so that you could exclude it when you're trying to get your amp post separation?
Yeah, so what we found is that didn't have anything to do with the table height, like where it was, because it's a threshold method, so it'll try to threshold anything below.
Right, but you were saying that for these patients, that sometimes the couch is included in the,
Yep.
like it's not being excluded
Yep.
from the body size, but
Yep.
you could just exclude it geometrically because you know where the couch should fall on the scout. For the when you're looking at a lateral scout to get the amp post separation, can't you just, you know where the couch should be on that image?
So I think your method is a threshold method.
Yeah.
It has a failure. I think what Debbie's talking about is if you were to exclude the couch, your threshold method would actually be closer.
Oh yeah, definitely. Yeah.
And if you already have it from metadata to do that, but you don't do the entire image, you actually do the threshold method on it more effectively.
Like, if we just go back
Oh,
to
yeah.
the picture.
Maybe I don't understand.
You could just exclude, like, you know from the couch height where the couch top should fall from this distance out. So anything from like that point to the left, you would exclude
Oh,
from
yeah.
your image and then just threshold what's left.
Yeah, no, I know what you're saying. So, yeah, then we didn't use, yeah. So we didn't, we definitely didn't do that because we just wanted to use the threshold method, and the ACR DIR doesn't recommend, like, we just wanted to use their method as they described it. But now that I'm thinking about it, there is a paper that will determine where the table height is in the image, even though it's not something that you can get from the metadata, but they know how to calculate it. No, sorry, you can get it indirectly from the metadata. So you'll have the information, you just have to do a calculation to remove it. But it's a good point because yeah, it doesn't really. I mean, the difference. If you look at the points, like on the graph there, yeah, like yeah, they're not too different from the line of unity. So
it's not correction anyway.
Yeah, right.
Okay.
That's a good point, though. Yeah, like you want your results to be as accurate as possible. So yeah, it may be something that we should look at if it becomes a problem, because we only looked at 48 pediatric abdomen and like 12 chest. So maybe if we're looking at more data and we find that it actually is a problem, then we would need to do a correction for sure. Yeah, that's a good point. Yeah. Yep.
You mentioned it's an ACR method, so all the institutions who have the ACR accreditation, do they always use this ACR method?
Yeah, just because it's accepted. Yeah.
Okay.
Yeah, they recommend that you use their exact method. These are all the studies that I've looked at so far that have tried to do this, have used this extraction method. I was actually talking to someone who, like, he was trying to use it for another purpose. He was having some problems with it because, as you know, like, even we have some issues with it as well. It's just for the extreme cases like this. I mean, you want to be able to estimate the dose to the bariatric patient as accurately as possible. And, like, a lot of these points here, like, they fall a lot lower than what you would expect. So, you know, you don't want to underdose the patient. And it's not like, you know, it's not like some of these points here which are not significantly different. Like, this point here is pretty different than what we would expect it to be. So.
What is the ACR with requirement?
Oh, like what's the what's the cutoff? Like, yeah, 20%. So, yeah, like a lot of these points are fine. I would argue that these ones are kind of cutting it close. So you have to be within 20%. That's the threshold, or the cutoff. Yeah.
I have kind of a stupid question, so it might not make sense. Which is, like, for image gently, whatever, like, and I guess also what this is probably what this is related to is you want to upfront measure what your patient's specific dose is going to be so that you can adjust what you're going to give them. But, like, just on the scanner itself, like, does that mean you don't use, like, auto MA type stuff, that you're just going to, like, how do you, because the scanner wants to do some variable thing, like, how do you enforce the thing that you want, like, just practically speaking on the scanner?
Yeah, so, I mean, that's why these groups are actively involved in reverse engineering a lot of these AC algorithms.
So they can put in a smart algorithm that does the same thing but more patient-specific?
Yeah.
Oh, so you can't routinely just do it on a commercial scanner now?
Right, yeah.
Like, you have to pick, either you're going to put in your MAs that you've determined are good on average, or you can use their thing, but they don't really work at the same time.
Yeah, and as I mentioned, like, some of these AC algorithms modulate only in the Z direction. Some of them do it in the XY, so they're different. I mean, the direction I want to go in is also developing my own AAC algorithm that will use this information. That's like a long way off, but I would like to go in that direction for sure. It just makes sense to me.
Scanners have, like, research modes where you can put stuff in?
Yeah. So, like, manual modes, yeah, and we've been using that as well for continuing this project. We don't necessarily use that on patients, so we just use one of the built-in methods that they have. So, yeah. Is that all? Well, yeah, thank you very much for coming. I hope you liked this talk. I know it's imaging, and you guys are in therapy, so.
we like it.
Yeah.
I love it.
This is a hot topic on the imaging side, so I think it was important to kind of give you this information. Yeah, so we're continuing this project here, which I'm really happy about too, because it's just it's specifically for the water equivalent diameter calculations. Like, that's really what we should be looking at, but we want to make sure that everything that we have up until now is validated and works perfectly, obviously. So, yeah.
Right, thank you.
Yeah, thank you. Thank you so much for doing that. I was like, oh my goodness.
Sure, we obviously need new batteries.
Yeah.
That was interesting. It actually